Hi class, Professor Smith here, excited to create a video on applying L'Hopital's rule twice to the indeterminate form 0 over 0 or infinity over infinity. Find the following limit. If necessary, select the most informative answer from minus infinity to infinity and does not exist. So when we substitute in, we can see that as x increases without bounds, so does 8 over x, and similarly with the natural log. And in the denominator, 7 to the x increases without bound, and then adding a large number is also going to increase without bound. So it's of the form infinity over infinity, so we can apply L'Hopital's rule. So we have the limit as x approaches infinity of the derivative of the numerator, which is a product. So I'm going to take the second factor, which is ln of x, and I'm going to multiply it times the derivative of the first, which is 8 to the x ln of 8. And I'll do that in a little thought cloud. If we have y equal 8 to the x, if we take the natural log of both sides, we get the natural log of y is equal to the natural log of 8 raised to the x power. But that x power, we can bring that power down. So that's really the same as x ln of 8. So we'll rewrite that as x ln of 8. And then we'll take the derivative of both sides. I'll give myself a little more room. We take the derivative of the left-hand side, we get y in the denominator, and then y prime. And then when we take the derivative of x ln of 8, that's just a constant times x. So the derivative is just going to be the constant, which is ln of 8. And then if we want to solve for y prime, we can multiply both sides by y. We'll cancel the y's on the left. And then we have y prime. And then we'll rewrite y with what it's equal to, which is 8 to the x. So we have ln of 8 times 8 to the x. And I'll go ahead and write that 8 to the x first. So I'll commute these two factors. So I'll have 8 to the x times the natural log of 8. So that's what y prime is. So just remember when you're taking the derivative of a to the x, which is a little bit different than e to the x, all you do is say, hey, it's the same thing, a to the x, and then multiply by the natural log of whatever the base is. Right? And then we'll go ahead and take the derivative of the second factor, which is 1 over x, and multiply it by a to the x. Now we'll take the derivative of the denominator. So we have the derivative of 7 to the x, and so we're going to get 7 to the x times the natural log of 7, and the derivative of x is just 1. We notice that we have an 8 to the x in each factor, so I'm going to factor out that 8 to the x. Uh-oh, I changed infinity to 8. Let me fix that. So we have 8 to the x times ln of x times ln of 8 plus 1 over x, all over 7 to the x ln of 7 plus 1. It doesn't look like anything's going to cancel that I can evaluate this expression. When x increases without bound, I have a to the x, which increases without bound, and then ln of x, which also increases without bound, but we also have plus 1 over x, which goes to 0. So it's not quite in the form infinity over infinity, but it really is. But let's just multiply top and bottom by x over x. And when I do that, when I distribute that x over x to the two terms inside, I'll get x ln of x times ln of 8 plus 1. And that is of the form infinity over infinity, because I have products of things going to infinity all over a product x times this expression in the denominator also going in infinity. So I really do have infinity over infinity. So I can go ahead and apply L'Hopital's rule to the expression before I multiply by that x over x. So I'm going to go ahead and erase that. So we'll go ahead and take the derivative of the numerator. So we have the limit as x approaches infinity of the second factor, which is ln of x, times ln of 8 plus 1 over x, times the derivative of 8 to the x. And 8 to the x is just 8 to the x, ln of 8, plus 8 to the x times the derivative of ln of x, ln of 8 plus 1 over x. So the derivative of ln of x is 1 over x, and ln of 8 is just a constant, so we'll just multiply by that constant. And the derivative of 1 over x is minus 1 over x squared, or minus 1 x to the minus 2. And then when we take the derivative of the denominator, we just have a constant, which is ln of 7 times 7 to the x. So we're going to get 7 to the x times the ln of 7. That's the derivative of 7 to the x. And then I'm going to multiply it by that constant, ln of 7. And then when I take the derivative of 1, I get 0. And that's the beauty. We started off with an x. And when we took the derivative the first time, we got a 1. And when we take the derivative of 1, we get 0. All right, so let's go ahead and factor out the 8 to the x and then distribute the ln of 8 times the first set of parentheses. And we don't have it. If we factor out the 8 to the x, we don't have anything to distribute. Then we will kind of get rid of some of the parentheses and hope that maybe this gets a little bit better now that we've gotten rid of the denominator so that it doesn't have two terms but just has one. All right, so we have 8 to the x. And then I'll distribute that ln of 8. So I have ln of 8 twice. So that's ln of 8 squared times the natural log of x plus the natural log of 8 over x plus 1 over x ln of 8. Well, that's cool. I have these two. That's like terms. And then I have minus 1 over x squared. All over 7 to the x, and then the natural log of 7 squared. Now, there's an interesting relationship between different functions as x increases without bound that describes which one grows faster. And we see that the exponential function, if we take 8 to the x over 7 to the x and simplify it as 8/7 to the x, anytime the base is greater than 1 and 8 over 7 is bigger than 1, that exponential function is going to dominate any logarithmic function or any power function. So let's go ahead and simplify. So we have the limit as x approaches infinity of 8 over 7 x times the natural log of 8 squared times ln of x plus 2 natural log of 8 over x minus 1 over x squared all over ln of 7 squared. And since that's a constant, I think I'll just write that ln of 7 squared that's in the denominator. I'll just write that as 1 over ln of 7 squared. And again, 8/7 is bigger than 1. And so we can see any base raised to the x power is always going to be greater than the natural log function. And that's always going to be bigger than any power function. So 1 over x and 1 over x squared. And that's true for x greater than 1. All right. So again, this base, or 8/7 to the x power, since that base is bigger than 1, is going to dominate. And so we have 1 over the natural log of 7 squared times the limit as x approaches infinity of 8/7 to the x times the natural log of 8 squared times the ln of x, because we can think of these two guys here going to 0. And we can see that this expression is just going to get bigger and bigger without bound, which is equal to infinity. But you know, we could have done this without even doing the L'Hopital's rule. So let's do that first. Well, let's take a look at that option. You know, we could have done this without using L'Hopital's rule. Let me show you.